Okay, so this talk is about spatially quasi-periodic water waves. Just some background on the things I've worked on maybe over the last 10 years or so. Oh, actually, first, this is joint work with my student Xinyu Zhao. And then parts of it are also joint with Bernard de Koninck, Olga can't even say her name, Trichenko, and David Ambrose and Jeremy Marzuola. But most of the work that I'm talking about today is joint with Xinyu. So, you know, for maybe this last 10 years or so, I've been developing numerical methods for solving two-point boundary value problems, mostly in fluid mechanics, like looking for time periodic solutions of various systems like water waves and vortex sheets. The methods are high order, so they're spectral in space. I usually use 8th order in double precision and 15th order in quadruple precision, so they're very high order in time as well. Through parallelization, they're pretty fast. You can compute the Jacobian quickly using either a GPU or like a supercomputer or something. And they're quite robust. One thing that's unusual about the way I'm doing shooting methods is that we pose them as overdetermined nonlinear least squares problems, and the overdetermined aspect makes them more robust, so it's not so delicate. Under-resolved modes don't end up causing the Jacobian to become singular. So the first approach that I developed, this was joint work with David Ambrose in 2009 and 2010, and then also with Nathan Kutz at University of Washington in 2011, was something called the adjoint continuation method. And the main idea there was to be able to compute gradients of the objective function using adjoint techniques by solving adjoint PDEs. And with that, David and I studied the time periodic solutions of the Benjamin-Ono equation, which is a really fascinating subject since it's an integrable problem. And we also computed a vortex sheet with surface tension that was time periodic. That was sort of my introduction to irrotational fluid mechanics. And then a couple years after that, I developed something called a trust region shooting method, where instead of solving adjoint equations, we solve the full forward problem for the whole Jacobian in parallel in such a way that it still actually works out to be really fast. And then my student, former student Trevor Potter, was working on generalizing that to solid mechanics problems. And one of the things he looked at are rapidly spinning either elastic or viscoelastic bodies, like tires on a drag racer. So maybe I should have included it, but we had this, I have this nice video of a drag racer racing down the road where the tire starts changing shapes and bifurcates into these alternate shapes. And Trevor's work was on trying to understand the dynamics of that problem. The work I did with Olga and Bernard is spectral stability of resonant traveling waves and Wilton's ripples, and that actually that's sort of a springboard into a lot of the work that I'm going to talk about today. I guess about a year and a half ago, I wrote a paper on harmonic stability of standing waves, and then I'm also working on a paper on subharmonic stability of standing waves. And mostly I'm today talking about spatially quasi-periodic water waves, both an initial value problem and the traveling wave problem. So this is a movie that I made when I was working on the vortex sheet with David Ambrose, and it shows really how amazing the dynamics of these fluid interface problems can be. Probably through Zoom it's pretty choppy, but what is shown is the fluid particles moving along with the flow. You have a vortex sheet in between with surface tension, and then the flow is shearing across, and periodically this sheet overturns without ever rolling up or self-intersecting, and it comes back to an exact replica of its initial condition at a later time. So that's something we did with the adjoint continuation method. And then with the trust region shooting method, I was looking at this Penney-Price conjecture, which is a really tricky problem because you're trying to study time periodic standing waves that become singular at some point along the trajectory. Penney-Price conjectured that this would form a 90-degree angle periodically, so right at that point where it reaches its crest, that the highest amplitude wave, that there would be this smooth bifurcation curve of standing waves that would terminate when the wave reached 90 degrees. And his intuition wasn't super sound, but I think there were some experiments by G.I. Taylor that showed that it does roughly do this, although Taylor had a funny comment where he said, I don't fully understand the reasoning, but it does seem to be true. This had been looked at by a number of people Vandenbroek and Schultz, I think, had a conjecture that it would form even a cusp. Mercer and Roberts thought it would form something that was sharper than 90 degrees. And when I looked at it really carefully with about 200 times the resolution as previous studies near the crest tip, it turned out that it doesn't form a corner at all. Like the self-similar arguments that Penney and Price were using didn't really work out. And it turns out there just is no limiting wave. The problem just becomes really oscillatory, and any branch, there's a bunch of branches up there near the supposed largest amplitude wave, and none of them actually forms a corner. So that was like a really interesting sort of math question in fluid mechanics that had stumped people for 50 or 60 years. And it turned out that with more resolution, it turns out that these resonances that I think people now understand pretty well with small divisor as a small divisor issue ends up preventing the self-similarity that works out for the traveling wave. Okay, so the way I've organized this talk, that's just some background of what I've done before. I want to talk about quasi-periodic solutions of the Benjamin-Ono equation. You can actually write them down explicitly, so it's a good way to define what is a quasi-periodic solution. And then I'll talk about traveling water waves and subharmonic perturbations of those. And Wilton ripples are a special case of those that we're generalizing to the case of irrationally related periods. And then I'll also look at finite amplitude bifurcations from periodic traveling waves to quasi-periodic traveling waves. And then we'll move on to, I'll just say a little bit, just some other work I've done on standing waves, something called a traveling standing wave, whereas as time evolves, it comes back not to its starting position, but to a spatial translation of itself. So that's a quasi-periodic in time and space solution with two quasi-periods. And then I'll also just, I have one slide talking about work I've done, sort of like a computational version of what Berti and his group has done, proving the existence of quasi-periodic water waves with more than two quasi-periods. And I'll just explain a little bit about how I approach it with three quasi-periods. And then the rest of the talk will be focusing on the spatially quasi-periodic case. All right, so with Benjamin-Ono, so Benjamin-Ono is sort of a model of interfacial waves, and it looks like ut plus ux minus huxx equals 0. So it's a lot like KdV, but you replaced one of the derivatives on the dispersive term with a Hilbert transform. And Benjamin-Ono has this hierarchy of stationary solutions and traveling waves, and then multi-periodic solutions. And they're all built out of these same things. So these phi hat of k beta are the building block solutions of all the time periodic and quasi-periodic solutions. And in Fourier space, they're beautiful. They just decay exponentially. Positive Fourier modes, there's some parameter beta it's a complex number less than 1 in amplitude. And the Fourier modes of this function are 2 beta to the k, where k grows, so they just decay exponentially. And then it's real valued, so if you change the sign of k, you'll end up conjugating beta. Those turn out to be rational functions of cosine, and I've drawn several of them here. So there's a family of them that basically depends on the amplitude. It depends how close is beta to the boundary of the unit disk, and then where this thing is left and right. Right now I've centered it at pi, but you can move it around by changing the phase of beta. You can build the stationary solutions by either rescaling using the Benjamin-Ono scaling condition, and you multiply the solution by n, and you also scale the space by the same factor of n. And it turns out that can also be written as just a sum of the ones without the n on them. So if you take the nth root of beta in this version, and you sum up over all those nth roots, you'll end up with the same solution. So it's a sort of a self-replicating function. So the traveling waves are obtained from these stationary solutions. Those just sit still, so there's no time. If you add a constant to the solution, it'll start traveling at a certain speed. And David Ambrose and I were looking at bifurcations from those traveling solutions to fully time periodic solutions. And we found bifurcations from any traveling wave, and there are these paths of solutions, and it turns out every path ends on another traveling wave. So I worked out the bifurcation theory of like starting on a given traveling wave, what parameters will actually lead to a time periodic solution. And it was a complicated process, but it turned out there were 4 integers and a number, a real number that governed the transition. And then you can even work out what other path, what other traveling wave will you connect to, and what are the bifurcation parameters of that wave. I had worked all this out. Around this time, I was starting to understand the problem is integrable, and there are other ways of representing these solutions. But I found a new representation that hadn't been looked at before in terms of these betas. So one way to interpret these betas is that they evolve in the unit circle according to a differential equation. This goes back to work by Case in the 70s. He was thinking about it in the upper half plane, but if you want periodic solutions, I found it was nice to apply a map to bring it into the unit circle. And so these particle trajectories, the number of particles is the number of humps in the solution, and they execute these periodic orbits in the unit disk as the PDE, as the Benjamin-Ono equation executes periodic orbits as a PDE on the torus. And my representation of all the bifurcations from traveling waves turned out that you can find the betas just by writing down a certain polynomial, which has some coefficients that you can write down explicitly. Plug in e to the minus I omega t into one of the slots. This was a polynomial in lambda and z. Solve for the betas at any given time, and those actually tell you what the amplitudes of the time periodic solution is. And my representation was different from a previous one in that it actually explicitly showed how these bifurcations occur. So when I did this, I think either Harvey Seeger or Mark Ablowitz pointed me to Dobrokotov and Krichever's paper. And it's a beautiful paper in which they generalize not only in the direction of well, not only to periodic solutions, but also to quasi-periodic and space solutions. So Krichever and Dobrokotov showed that, so first of all, I'm defining a quasi-periodic solution here. So you have some function that's periodic on a higher dimensional torus, and you slice through that with some wave numbers kappa and some frequencies omega, and then you try to construct a solution out of that. So traveling waves look like f of x minus ct. So that's a special case where n equals 1. Standing waves, you can set up n equals 2. And these two found this whole hierarchy where you pick n parameters, or actually 2n parameters, looks like 2n plus 1 parameters for the amplitudes, and then a bunch of phases, and you'll end up with these multi-phase solutions of Benjamin-Ono. It's not at all obvious that these are the same solutions that I had, or mine are a special case of these, but it does turn out to be true. And so the question is like, so this is true, it's an integrable equation, so it's not so surprising that it would have this hierarchy, but are there analogs for the water wave equations? And since this is supposed to be a model of interface problems, and other model equations also have these quasi-periodic solutions that would model water waves directly. It's a good question. Are there quasi-periodic water waves? So I'm going to go through now as sort of a high-level summary of the kinds of things I've looked at, and then focus in on the quasi-periodic traveling problem for the second half of the talk. So the first one everybody's familiar with. This goes back to Stokes in the 1880s, actually 1840s, but he revisited it in the 1880s. So here we have a pretty sharply peaked traveling wave that I've plotted down there. But the basic condition of a traveling wave is that eta of xt is equal to eta 0 of x minus ct and phi 0 of x minus ct, where eta 0 and phi 0 are just some fixed functions of 1 in one dimension. So that's an n equals 1 quasi-periodic solution by our definition up here. For a standing, okay, so then what I'll do is talk about n equals more than 1, so n equals 2, traveling waves. So I'll be looking for spatially quasi-periodic traveling waves where you have a two-dimensional torus, and then the solutions are obtained by running through this torus in some irrational direction. So you go, for every unit to the right you also go up by some value k, where k is irrational, and see if there's some two-dimensional function on the torus, so that when you extract one of these one-dimensional functions as a function on the whole real line, it actually satisfies the Euler equations. So that's actually that's perhaps the main goal of the talk, is to show that these do exist, and how can you compute them. So I think there are basically two ideas that I have for how to search for these things. One goes back to work of Chen and Safman, who noticed that that there are these period doubling and period tripling, period tupling bifurcations from the basic branch of traveling waves that give you other traveling waves that have longer periods. So here's one where I think the middle panel is a traveling wave where he's plotted 3 periods, and then he found a bifurcation from some finite amplitude wave where like every third wave actually goes up and the other two go down. And he in this paper, he found two different waves, one with two periods and one with where it's a period doubling one and one where it's a period tripling one. And this is the period tripling one. So then later Safman's student, Fourier, in his PhD thesis at Caltech, was looking for symmetry breaking waves. All of these turn out to be symmetric. And he had to go through like 3 internal bifurcations before he finally found one that was symmetry breaking. But he did eventually find one, although curiously, all of the figures are just hand-drawn in his thesis and it was never published. But I believe that this is actually true, that there is you can follow these 3 branches. Like maybe this bifurcation diagram was computed, but these were all hand-drawn. I think that was from 1986, that thesis. But it's a really interesting problem. Like how do you find these other paths of solutions? And then the other motivation for looking for these quasi-periodic traveling waves or getting some idea of where to look is the Wilton ripple problem. So work I did with Olga and Bernard about 4 years ago, we were looking at the subharmonic stability of Wilton ripples. So these occur when the sort of standard Stokes expansion encounters a resonance where you end up trying to divide by 0 when you're computing the next order in the expansion. And it turns out when it's at exactly the resonance, you have to bring in the higher harmonic at a lower order. So in this case, we were looking at a k = 10 harmonic, so that the 10th wave number was resonant with the first wave number. And exactly at 10, the slope ends up being 8 instead of 10, relating eta hat 10 to eta hat 1. And in this picture, I'm just showing what happens as you approach that resonance. And it turns out you do actually, I mean, all of these have slope 10 until you hit exactly the resonance, but like the slope 10 curve moves up and lands on the slope 8 curve in the limit. So this is a case where you have this resonance condition and k is an integer. So our question, Shinyu and my question was, what if k is not an integer? Are there still like solutions that would bifurcate from the flat rest state that would involve multiple wave numbers at leading order or at lower order? So that interestingly, that's very different than what happens in the standing wave problem. In the traveling wave problem, you lose one of the pure branch solutions. It just disappears. Whereas in the standing wave problem, you can get these resonances where both pure branches still exist, but then a third branch shows up when you hit resonance. I couldn't find my 2D solution where it actually has a really nice, beautiful second branch that's coming in off of the origin. But I did have this 3D one where this solution here is sort of a nonlinear superposition of these two 2D solutions. So those are 3D standing waves that I worked on with Chris Rycroft. I think this was in 2013. So the traveling wave problem is very different than the standing wave problem, it turns out, for these resonance conditions. So returning to the question that I was looking at with Bernard and Olga, we were looking at stability of the Wilton ripple problem, and Bernard was talking about this yesterday somewhat. So what we're doing here is just looking at you linearize around the traveling wave. So the traveling waves are over here. This has wave depth of 0.05, so it's pretty shallow. And we're still looking at the k = 10 resonance. So when it starts growing in amplitude, you'll see, I don't know, I think it's something like 10, but maybe it's more oscillations there. So each of these you can look at stability of subharmonic perturbations, and then we find these unstable directions. And so another motivation for studying quasi-periodic solutions, especially the initial value problem, is to see where these solutions go if you try to evolve them for a long time. So this picture is from my paper with Olga and Bernard, but we computed it just by taking the linearized solution and evolving the linearized equation. And eventually the perturbation grows, although we had to wait a long time for this one, which was almost stable. So after 1 million cycles of this thing, the perturbation has dominated the solution. But by that point, the linear equation is no longer relevant. So a good question is, if you have these unstable directions to a quasi-periodic bifurcation, like what will happen if you evolve that over a long time? Will it have some kind of periodic recurrence? Who knows? So we need some numerical method for solving the initial value problem to explore what happens with these subharmonic perturbations that turn out to be unstable to find out their long-time dynamics. Okay, so those are the traveling waves. Here we have a standing wave. This is one, I think I showed you this movie earlier in the talk. So we can think of this as being in this framework with two quasi-periods where you define eta tilde just by the condition. You just define it through the equation eta. You actually take this and write it down the other way. Normally you think of a standing wave as a wave that at the time capital T comes back to its initial condition. So as soon as you have that boundary condition at the later time, you can define a function on the torus through this formula, and then you actually have put it in this framework. Although the way I compute it is as a shooting method. So what I put in the box is more like the approach that I have been taking for time dynamic problems. Traveling standing waves are another variant, which is still quasi-periodic. And now what happens is you come back to a spatial phase shift of the initial condition. So at the later time, the wave that started off with the peak showing up at the origin, the peak is now showing up shifted into the domain. This one travels pretty far each wave, so so it made it about a third of the way already in just the number of cycles you've seen. So that's a pretty different type of wave than the pure standing wave. And it turned out that the initial conditions you search for these have sort of a different symmetry than you usually set up with the standing waves. Although when you set it up this way, the standing waves end up living in this hierarchy. It's just not the usual set of symmetries to set up the problem with in a shooting method. So these you can also find a torus version just by defining eta tilde after you've figured out what I guess this is what I put in the box is how I actually compute them, and then the equations in blue here are how you can define the periodic function on a torus from the actual solution that you compute. Okay, and then the last part of the introduction is based on, it's a numerical approach to ideas that Berti and Montalto published in 2016. And let's see, there have been a number of papers since then. Berti, Baldi, Berti, House, and Montalto, Berti, Franzoy, and Maspero, and very recently Fiola and Giuliani all looked at quasi-periodic water waves in this sense. So my idea is to try to turn this into a shooting method as well. So that's not the approach they took. But what I try to do is you introduce another parameter. So you have a whole family of traveling waves. So this theta direction is a parameter that parametrizes a bunch of traveling waves. Each of them is going to evolve vertically in this box up to some time t that we have to find. And then at the time t, the solution that you get coming up from this parameter has to shift over by some amount 2 pi minus gamma to land on this one, and then it'll move up, and then that'll shift over to the next one. So if you keep following this thing, you'll get a solution in time that marches through this torus that is a solution of Euler. It's a periodic in space, but quasi-periodic in time. And I decided it would take too long to explain this in too much detail other than to say that there have been rigorous proofs of existence. And we're trying to develop a shooting approach, which uses a lot of their ideas for handling the small divisors. Actually, in the in the shooting approach, in the numerics, you just hope the small divisors don't cause problem. And you see them coming up, but often you can find a very accurate solution, albeit an approximate solution on the computer, but often to many digits, like 30 digits or more. Okay, so those are the temporal quasi-periodic problems that I've looked at. So what I want to do for the rest of the talk, and I guess I have like 15 minutes or 20 minutes, is talk about the spatially quasi-periodic problem. Maybe I'll pause here and just check in. Is it clear what the questions are? So we have all these different types of quasi-periodic solutions. So far, I've mostly been showing you movies of time-periodic things. But now the idea is, what if you look for spatially quasi-periodic solutions of Euler? How would you go about looking for those? Okay, so first I need to explain the equations of motion. I guess it's funny to wait for half the talk to do that, but I was assuming almost everyone in this audience actually knows the Euler equations. So in general, you could even have obstacles, but I just had this figure available, so we won't have obstacles in this talk. So you have a free surface gamma, which is evolving in time. I'm parameterizing by c of alpha plus I eta of alpha at a given time. The curvature is kappa. So when you've parameterized the curve generically like this is what the curvature looks like. The Bernoulli equation so if I'm assuming potential flow, then you can integrate the Euler equations up and end up with Bernoulli. And so this is what the equations of motion end up looking like for Euler. I have basically three approaches to the representations of the curve in space. One, so I guess all of them you can write this way: zeta of alpha t. If it's a two-dimensional problem, you can embed it in the complex plane. So xi and eta will be their real and imaginary parts, or the x and y components. And so if you take the alpha derivative, it'll give you the tangent vector. And so you can write that as s alpha times e to the I theta. So theta is the tangent vector with respect to the horizontal, and s alpha is the rate at which you're parametrizing, or you're traversing the curve. So one method, which is I think the most standard one, is a graph-based representation where zeta of alpha is just going to be alpha in the x direction and eta of alpha t in the y direction. So this is just, eta is just a function of alpha, and you don't have to worry too. It's the simplest formulation of the problem. So xi of alpha t is just equal to alpha. So if you let's see, did I say what the, I guess I should say what's going on with the zeta t dot n. So that's saying that the normal velocity of the fluid is dictated by the fluid velocity. So u dot n is the normal velocity of the fluid, and then zeta t dot n is the normal velocity of the curve. So no matter what your parameterization is, you need to have zeta t dot n to be equal to u dot n to be actually modeling an interface problem. So the picture here, u is defined to be zeta t dot n, and that should be equal to d phi dn. So that's our normal velocity. And then you break zeta t into v plus iu. Those are the tangential and normal components of the fluid. So the first method to compute v, the tangential velocity, it turns out v has to be equal to eta alpha u in order for xi t to actually be 0. So I have xi of alpha t is equal to alpha. So xi t is therefore equal to 0. And if you write down what is xi t from this equation, take the real part of it, and just work it out. For that to be 0, you need v to be equal to eta alpha times u. And so then eta t ends up being equal to square root of 1 plus eta alpha squared d phi dn. So this is our very familiar Dirichlet-Neumann operator. So from our sort of generic formulation, if you just ask that xi of alpha t remain equal to alpha, you'll end up with eta t being the Dirichlet-Neumann operator applied to the velocity potential. The second approach is due to Howlow and Grubb and Shelley. The idea now is to, instead of having everything move vertically, to try to keep the curve parameterized with respect to arc length. So we keep s alpha of t equal to a constant. That constant can evolve in time, but at any moment s alpha is equal to, doesn't depend on alpha. And so if you work out what that means for, as a compatibility condition, you can take the time derivative of zeta alpha, the alpha derivative of zeta t, and match them, and you end up with conditions on what has to be happening with the tangent angle and with s alpha in time. And so you end up computing u and v by solving some fluid equations. You have to solve for the fluid velocity on the free boundary, and then s alpha t and s alpha theta t will actually dictate what the evolution of those two variables are. So instead of recording eta directly, you record theta. You record theta to parameterize the curve, plus this one number s alpha. This is in detail how you reconstruct the curve from it, and what I'll just show you is that it's a really flexible method. You can do things. So here's the one problem where I do have a multiply connected domain. This is joint work with Ambrose and Marzuola and Kamasa, the main collaborators. So we're looking at free surface flow over obstacles. Since they have a machine in their lab with an obstacle in it, we're trying to understand fluid flow around obstacles. So the Howlow and Grubb and Shelley approach is flexible enough to handle these obstacles. You really couldn't do that with a conformal mapping approach. So here's a case where it still is great to use complex analysis, but you need a different method than conformal mapping. So now finally the third method is conformal mapping. Our idea now is you just like in the graph approach, you want to have just eta be the main variable that you evolve. So but instead you determine xi. Xi should be related to eta by the Hilbert transform. So you either can construct eta from xi by subtracting alpha from xi and taking a Hilbert transform, or you can say that xi is equal to alpha plus Hilbert transform times eta. And that's almost true, but there's one more constant that you need when you do that. So okay, so you go through this. This goes back to Dyachenko and Zakharov in the 90s. It's a really beautiful method that speeds up the ability. It allows you to compute free surface dynamics much faster than boundary integral methods can usually be done. So okay, so the complex. So in this approach, you also define a complex velocity potential, and you try to figure out how. And then the real and imaginary parts of that are the regular velocity potential and the stream function. Those will also be related by a Hilbert transform. And the beautiful thing about the complex analysis is that you can take a tangential derivative of the stream function to figure out the normal derivative of the velocity potential. So that allows you to just do everything on the curve without solving any PDEs inside the fluid domain, or rather they're sort of solved for you by this Hilbert transform and the conformal mapping formulation of the problem. So this was, I would say, the big idea of Dyachenko and Zakharov is that ZT over Z alpha, which I interpret to actually be the tangential velocity divided by S alpha and the normal velocity divided by S alpha. That's not how they explained it, but it's essentially what they're doing. It turns so that shows that V over S alpha and U over S alpha actually are the real and imaginary parts of a analytic function in the lower half plane. So those should actually be related by the Hilbert transform. So this allows you to compute the normal velocity from the tangential velocity or the tangential velocity from the normal velocity just by applying a Hilbert transform. And if you do that, it turns out that the equation that you need for Xi to satisfy is automatically satisfied if eta satisfies the second version of the equation, because you can interpret this matrix multiplication as complex multiplication of analytic functions in the lower half plane. That was an argument that Shinyu and I, it took us a long time to figure out, like, how do you know Xt satisfies this equation if all you do is impose the A to T equation? And it turns out that this matrix equation that you get from a kinematic condition is exactly the same thing as just multiplying two things that you've built to be an analytic function in the lower half plane. So they're therefore automatically related by a Hilbert transform. So then you can reconstruct C from eta just by this, alpha plus x0 of t plus h times eta to figure out Xi. And the one constant of integration is this Xi0 of t. And there's one additional ordinary differential equation that it has to satisfy, where you have a constant C1 available to you. You just have to make sure you put it in all the right places. So any choice of C1 will lead to a solution of this. That x0 is basically deciding what you're calling 0 for your tangential parametrization of the curve. Okay, so once you've figured out how you're going to represent the curves, you have to figure out how to solve the Laplace equation in the fluid to impose incompressibility. For methods 1 and 2, I use Cauchy integrals and potential theory. So basically you write down an ansatz for what you think the solution is, and you have to solve some integral equations to find the normal derivative given the Dirichlet boundary condition. But in the conformal mapping approach, it's basically automatic because you can compute the stream function from the velocity potential just by taking a Hilbert transform. So if you write down the Bernoulli equation that's supposed to be holding on the free surface, you can write it as a change of variables in terms of normal and tangential components. And it turns out you can just write it down as a projection of an equation involving the stream function and the velocity potential and some Hilbert transforms. So there's no, you've completely gotten rid of the fluid, the problem that you have to solve in the lower half plane. Everything is now encapsulated in this Hilbert transform. So this is what the equations of motion look like for the conformal mapping approach. It's kind of ugly, except that, I mean, the equations are ugly, but it's nice because you only have Hilbert transforms. You don't have to set up any boundary integral problems to solve these equations. Okay, so those are the equations of motion. So far, I've sort of been pretending like it's a periodic problem, but everything actually works in the spatially quasi-periodic setting as well. If you think about Hilbert transforms for a spatially quasi-periodic function. So a spatially quasi-periodic function is a function where you have a higher dimensional torus in Rd for any function u on the real line, I'll put a tilde on it to look at the torus version. You have some wave vectors k, and throughout this talk, that vector will be 1 comma k, where k is a scalar. So let's just mostly focus on the d equals 2 case. So you're slicing through a torus function along the 1k direction. As you move along in alpha, you slice through this thing, and you can represent the solution u through a Fourier representation of the torus version. So u tilde is defined on the torus. You look at its Fourier representation, and then when you extract through in the 1k direction, you'll end up getting a quasi-periodic solution of one variable. So now the question is, like, if I'm going to do analytic continuations in the lower half plane, as you do in the setup for the conformal mapping, you can do the same thing, but the condition is, instead of having integers here, you have these irrational things, j1 plus j2k. So if those are less than 0, then you include it in the sum, and if they're greater than 0, you discard it, and you put a factor of 2, and that thing will end up so you're given the real part of this function f. You want to figure out what is the analytic function in the lower half plane that has that restriction to the real part. And you do the same thing you do in the case of a periodic problem, but you have these j1 plus j2k replacing the usual either j or k quantity there. This analytic extension turns out to be quasi-periodic on slices of constant depth. So if you go to a depth of beta, where you're looking at alpha plus I beta when you unwrap it under the real line, you can, alpha still is the restriction of a two-dimensional torus function at any depth to extract your analytic extension to the lower half plane. There's still a torus function at any depth to extract it. The tricky part about this is that you have these torus functions, but it's only once you've extracted it, is it an analytic function? So that I think was a hard part of figuring out how to formulate this mathematically. To extract the imaginary part on the real axis, you still define a Hilbert transform, and it works the same way, but you replace our usual sign of the wave number by j1 plus j2k. So that's the wave number of the quasi-periodic of the one-dimensional function that you extract from the torus. Yeah. Okay. So then we have a torus version of the Hilbert transform, where you have an operator you can apply to the two-dimensional function, so that when you extract that, the one-dimensional extraction of that is the same as the Hilbert transform applied directly to the one-dimensional function using the usual definition of the Hilbert transform. So all you're doing is taking the sign plus or minus 1 or plus or minus I of the wave number of the extracted function. So for any wave number k, it's a different Hilbert transform though. So it maybe needs a subscript k on it. We also need projections. If you have this infinite function that isn't compactly supported or something, to figure out what its mass is, you have to average it somehow. So the most natural thing to do in the quasi-periodic framework is average the torus version. And then for time stepping, I use a Runge-Kutta method, possibly with something called a small scale decomposition with an exponential time differencing scheme to sort of extract the leading source of stiffness from the rest of the problem. Okay, so then we have a pseudo-spectral approach to representing the functions. This is the time stepping the initial value problem. So you can represent the function either in its Fourier expansion or on the grid, on the torus version of the grid. So you just go back and forth between the torus function and the Fourier modes to compute. You compute derivatives in Hilbert transforms in Fourier space, and you compute all of the nonlinearities in the evolution equations in real space on the torus. And then, so otherwise it just looks like a usual pseudo-spectral method. So here's, I only included one solution of the time dynamic problem. Since the conformal mapping approach does allow overturning waves, we decided it would be fun to look for a solution that starts off with vertical tangent lines. So it's a periodic wave initially, but you set it in motion with a quasi-periodic velocity potential that causes each wave to do something different. So this first wave actually moves forward and starts to overturn to the right. The second wave actually moves backward and starts to flatten out. And as you move along the wave, it's an infinite wave train where every crest does something different. And roughly half of them, I guess, will overturn, and the other half will sort of flatten out. But all of them do so in different ways. So it's kind of a neat idea that you can end up with with a single solution that's doing all these different things that is quasi-periodic in space for all time. This is what it looks like in the torus version. It turned out to be a huge calculation to actually end up with an overturning wave. You need a lot of Fourier modes to get a conformal mapping to actually almost overturn or to overturn fully. And then we had to add another dimension to allow the variation in the alpha 2 direction. Initially, it's only a function of alpha 1. But then because phi wasn't, phi did have an alpha 2 component to it, it required a lot of modes to evolve that. It actually took 4 days on my computer to evolve that overturning wave. For the spatially quasi-periodic problem, a nice formulation of it is just to go into the traveling frame and look at the stationary Bernoulli problem. That is equivalent to what we just did. It's sort of a long derivation to show that the two things are equivalent. But the equations of motion for the traveling wave are pretty simple. At least one formulation of them looks like this. So what we'll do is look for a quasi-periodic function eta. If you know your conformal mapping, you actually also know the velocity potential. Just z minus w turns out to be the velocity potential. So that reduces the spatial problem, or the spatial problem to just finding eta. And then these are the equations that you're trying to solve on the torus. The question of where to look for these solutions is a difficult question. I guess I'm almost out of time, but the idea that we had was really based on having worked with Olga and Bernard on the Wilton ripple problem. Is this dispersion relation at zero amplitude can give you multiple wave numbers that travel at the same speed. So to leading order, you can assign those two to have whatever amplitude you like, and then try to solve for all the other Fourier modes based on these two. So this dispersion relation, to find those two wave numbers, I'm going to set it up so k1 is equal to 1 and k2 is equal to k. And then that tells you what the wave speed and the what the wave vector should be. I actually end up turning it around and freezing k to be some irrational number and then solve for the surface tension. I wasn't sure what to think of, like having k be varying, where sometimes it would be passing through rational directions. So instead I had the surface tension depend on k. And so if you do that, if k is rational, it's the classical Wilton ripple problem that I had showed you earlier. And then if k is irrational, it gives us a good starting guess. So what we do for to search for traveling waves is set up this big two-dimensional overdetermined shooting problem. It's not time dependent anymore, but you still have to solve for all these unknown Fourier modes. And so what we do is have the rows of the matrix be the values on the grid and the columns be Fourier modes, and search for Fourier modes that actually enforce the I guess it's this computer that enforce the traveling wave condition. So it ends up being a huge problem. Like there's a lot of unknowns. I use the Levenberg-Marquardt method. Here are some of the Fourier modes at low frequency that Shinyu and I computed. So these are fairly low amplitude waves. This is what the waves look like. You can see, especially when you bring in the two modes at equal orders or equal amplitude, the wave is clearly quasi-periodic. It's there is a strong component of k equals 1 and k equals 1 over square root of 2 involved in that solution. And this is what the torus versions of those two functions look like. So the actual calculation computed this whole family of solutions, and then I'm just showing some slice over some finite distance along that torus. And here we're looking at how do tau and c depend on amplitude. And so we have left the linear regime by in this calculation, which wasn't particularly large scale yet. And here's our time evolution using our time stepping code to make sure it actually is a traveling wave. And so here I was looking at the various time stepping methods on this solution where we know the exact answer as a test problem for the time stepper. And the small scale decomposition does allow you to take much larger steps. And the Runge-Kutta method all of a sudden is okay, but because the problem is only stable for high surface tension with small enough steps. And then the last thing is, it'll just take me like 1 minute. So we're looking at finite amplitude bifurcations. So this is the generalization of Chen and Safman. Here is this curve of periodic traveling waves. And so what Shinyu and I were doing is looking for some large amplitude perturbation of that finite amplitude wave that goes into a quasi-periodic direction. So we look at the Jacobian of our solver for periodic waves and look for additional places where where it has a new kernel. Once you have a kernel, you have a perturbation direction to search. searching for that, I found this is the wave, the periodic wave that should have a quasi-periodic perturbation. It has 500 active Fourier modes, so it's going to be hard to compute, expensive to compute, but it gave us a direction. And then there were a lot of unknowns, so I truncated this at 50 in the J2 direction and 50 in the J1 direction, but actually the J1 calculation went out to about 500. So I think there were 100,000 unknowns or something like that. And then I just trying to figure out what can I show you. But each of the traveling waves, each of the traveling perturbations has its own, or has a nice, has a different behavior near the crest peak. Each of these is actually a traveling wave, and what I did in this figure is try to show lots of different wave crests of a single traveling wave that extends in both directions to plus or minus infinity. I think that might be my last slide. So I probably, instead of summarizing, I'll just thank you for your attention. And if there are any quick questions, I probably could answer them.